So our speaker today is Rodrigo de la Jara, science enthusiast. Rodrigo de la Jara is dedicated to enlightenment values and emphasizing empirical evidence over ideology or dogma. He belongs to the Greater Edmonton Skeptic Society and other intellectual organizations. Rodrigo has a wide educational background in molecular biology, psychology, microbiological sciences, education, and computer science. He works as a software engineer, likes to do high dynamic range photography, especially when traveling, and he loves having discussions with rational people. Self-talk, everyone.
The reason why I asked for questions at the end is I have a lot to get through. I'm going to do, hopefully not having to rush, but it's going to take quite a while. And it's all kind of really important, man, to put a bunch of stuff into this. It's really hard because most of these topics you have, synthesis classes that teach you it over a day or two. I'm going to do it in a minute or less for most topics. But if I misspeak, please raise your hand and tell me, because then everyone benefits from getting things right? Okay, so this is based on one paper that came out that proved mathematically that most things are wrong. When I've told people what I'm going to be talking about, they look at me like, yeah, right. You probably don't know what you're talking about. And like, start explaining it and say, oh, okay. So it's very provocative. The first time I saw the title of the talk, the paper, I was like, what the hell? But it turns out to be true. And it's has to do with Bayesian probability. First I'm going to start, so everyone kind of, as a refresher, hopefully you've all taken stats before, but you understand what a normal curve is. Here's an example of a few normal curves, that's what I had handy. We're going to talk about standard deviations throughout this thing, so you better understand what it is. Here are standard deviations, right? There's a normal curve. It's the area under this curve is equal to 1. 100% of all possibilities are under that curve. But between -1 and +1 standard deviations, you have 2/3 of the probability that will be in there. And then between -2 and 2, you have 98%. These are rough numbers, by the way. And then -3, +3 would be 99.9 nodes, correctly. Okay, so you can see the standard deviations are 1, 2, 3, 4, 5, whatever. But the measure here, it's IQ, it could be height, it could be whatever. Any experiment will have its own measure, right? It's going by 15 here, right? No standard deviations is 15 IQ points. That sort of thing happens for all kinds of stuff, and because it's a common, well, let me say denominator is repetitions for me, but standard deviations are a way of kind of talking about all of these differences from the average kind of thing. I mean, in a very general way. We see that it's used later on. Well, hopefully you have some idea what we're talking about here. Okay, first thing is correlation. This is very important, and I'm sure you've heard of it before, but I'm going to say it again. It's, how frequently one thing occurs when another thing occurs. There's ways to state it as well. Correlations can be positive or they can be negative. Two things can go up together, or if one goes up, the other thing might go down. It's a negative correlation. I'll show you some diagrams later on. And here's some descriptors as to correlations. Large, moderate, small, or negligible. And I'll show you some other descriptions of other sizes of measures, so you get an idea of when you're looking at studies, when you're reading about studies, hopefully in a blog or whatever else, you have some idea as to whether or not you should think something's important that you can report it on. So let's start. And here's examples of correlations. perfect negative correlation, perfect positive correlation, and then stuff in between. Okay? I think it's better than the descriptor in terms of giving you an idea as to how much of a relationship there is between two variables. Okay, you probably heard this 1,000 times from your profs and say it's so important. Correlation is not equal causation. A could cause B, or B could cause A, or A and B could be consequences of a common cause. And there might be no connection between A and B, like coincidental. One example of that is the flying spaghetti monster theology, that global temperatures have been going up at the same time as the pirate populations have been going down. So we need more pirates to be able to solve the global warming problem. The species, right? Okay, p-value. This is something you should know about, but it's being phased out in some areas of science. Its probability of, we have confidence in the well, how likely it is that you get some value more extreme than that. Basically, quantifying the strength of the evidence against the null hypothesis in favor of the alternative. So a null hypothesis is that there's no effect usually in alternatives that you're really as a scientist trying to prove. And it is taken as a measure of how sure you are that the results you got the experiment are true. But this is actually problematical, and the APA has deprecated this in favor of confidence intervals. There's a video online that I wish I could show, but it's too long. It shows you how p-values jump around depending if you rerun the experiment over and over again with the same number of subjects, etc. How the p-value changes for an experiment from 0.001 to 0.01 to 0.5, whatever. And it's just amazing to watch. People base so much of their credence on whatever study based on p-values, but it's a really weak way of assessing whether something is, you can have confidence in something. But anyways, here are some descriptors again. Generally, if you don't get p-value of less than 0.1, which is 10%, you fail. You haven't disproven the null hypothesis. You pretty much are not going to get published. You get that. Here's a lead, 0.25 to 1. You might go to get published in this. I think some psych papers get published with that sort of evidence. And the most common value is 0.05, which is 95% confidence. And I don't know if you guys watched the announcement of the Higgs boson discovery. They had a 6 sigma result. Remember that for this, you need 3 sigma, which is the first curve I showed you. So they went way beyond that. That's physics. They could do that. They could get tons of data and a really good p-value. It's much more expensive to do in psychology or especially medicine. Like I said, it's a bad way of gauging the practical significance. There's something called statistical significance, which is what this p-value I was telling you about describe. Usually you want 0.05 at least. But practical significance, it tells you practically, using the same word again, practically nothing about practical significance. You want to have an effect size to gauge that instead. And like I said, the APA has changed the standards from using p-values to confidence intervals because confidence intervals give you way more of an idea of where your might even give you an idea of where your p-value is going to end up in. Because it's just a range of those. You'll be an experiment. This is one measure of effect size, which I was talking to somebody, they're taking statistics, didn't know about. I didn't know this after taking second year statistics. I only found this out by being a skeptic, looking into studies, and learning about whether something doubling your risk of X, cancer, whatever, is that really something to be worried about? In terms of effect size and whatever else. So that's where I learned this, and I think a lot of people should know about this stuff. Like I said before, you need to know about standard deviation because it gives you the difference between the means divided by the standard deviation. Okay? So how much is the change? Instead of p-value, which tells you how confident you should be in the results. Because, for example, if you're giving a drug or some other intervention, if it barely budges you, it might double whatever value, but that doesn't actually have a real practical effect. Who cares? Right? You're wasting money on something that barely helps at all. But the effect size is a better measure of something practical benefits or something. And these are the different descriptors for small, medium, and large effects, which you can read there. Okay, now, as to the title of the talk, most studies are wrong. It's based on Bayes' theorem. This is very basic. I'm not going to give you the whole formula or the various formulas for that, but hopefully some of you have some familiarity with odds. If you don't, odds are not quite, converted to fractions are not quite fractions. For example, if you have a 25% chance of something, you have a 1 in 3 chance. Because 25 is a quarter, right? 1 chance that will happen, 3 that won't. So it's 1, 2, 3, or colon 3. Okay? And then you can switch back to fractional again, right? You have a 1 to 3 odds ratio. You put the 1 on the top. On the bottom, you put 1 plus 3, which is 4. So 1 over 4, which is 25% again, right? See how that goes back and forth? That makes it easy to calculate these Bayes' theorem calculations, and also what's used in poker and other things to quickly do stuff in your head, make decisions. And by the way, poker is, you're not good if you're not using Bayes' theorem in poker, whether you know it or not. So yeah, the posterior probability is equal to the prior probability times the likelihood. And here we'll see what these things mean with an example. So example is initially it's equal likely that a conversation is held with a woman versus a man. The prior odds of a woman versus a man are 1 to 1, because that's the population is about 1 to 1, right? If you know nothing else, on the left, it's the prior odds. But the chances are that a man or a woman have long hair are 25 to 75. 3 times more likely that a woman has long hair than a man. So likelihood ratio Bayes factor is 3 to 1. So you could use that very conveniently, 3 to 1, and then use our prior hours 1 to 1, and just multiply them across. 1 to 1 is easy. It's the same. So 3 to 1. So the likelihood that you're talking to a woman, if the person had long hair, is 3 to 1. Okay. So instead of just simply knowing, okay, somebody talked to somebody, 50-50 chance it's a woman or a man. If you know the fact that they have long hair, you can improve the chances of being right by using the Bayes' theorem. Okay? This was used to determine that most things are wrong. But before I go into that, I'll show you this joke. Hopefully you might be able to understand it now. This is what I told you. Read it. Does anyone know why the Bayesian is willing to make that bet? The one's going to guess? So yeah,
He's using prior information.
yes.
See the prior.
Yeah, I mean, how often is it that the sun explodes? Right? It's very effective. Versus the chance that it's going to lie to you, the detector's going to lie to you. The difference is astoundingly different, right? Almost infinitely bigger that, the things lie to you. But frequentist, just says, oh, I'm just going to go by straight now that's feeding out to me, and I'll apply my p-value blindly, and there we go, that's my conclusion. Okay? So, a frequentist would say that only 5% of studies work. They're using the 0.05 confidence p-value. But if you know other stuff, as a Bayesian, you could say, no, it's not right. One biggest problem is that there are many more false hypotheses than true ones. Many, many more. Just think about anything like your height. Whatever number that you have for your height. There's an infinite number of wrong answers for that, isn't there? Right? And we talk about medicine. There's all kinds of stuff to eat. And even the stuff we eat. A tomato isn't just a tomato. It's a tomato with a bunch of different genes, produces a bunch of different proteins, with a bunch of different bacteria or other organisms on it. Any one of them, well, maybe I shouldn't pick tomato, but let's say that somebody was claiming that this certain tomato could cure your cancer. You wouldn't know which one of those molecules is the thing that actually does that. Which types of tomatoes it is, which is determine which molecule it is to know which tomato has it, whatever. Or red wine is a better example. Because resveratrol is in red wine, and the last things you track it down to that one thing, right? We have all sorts of red wine. Some have more of that substance, some have less. And that's just one thing. There's so much stuff that can affect our health. You can make so many hypotheses. Just like the height example. There's so many more that could be wrong, where they're the ones that are right. Then you get the problem of, basically, if you're trying to determine what it is that's causing something, let's say you know it's red wine, you don't know it's resveratrol yet, that's what you're trying to find out. There's tons of compounds in wine. You can test all of these, one by one, and each one, the 0.05 confidence interval, has 1 in 20 chance of coming out positive when it's really not. Okay? And the more you do it, the more chance it is you're going to get some false positives, right? Now, that's one layer. One experimentalist looking at one substance, wine, counting all those possibilities. But then there's more because other researchers doing the same thing on top of that. Maybe on the same substance wine. On top of that, there's multiple intervention substances, diseases they're looking at. You just multiply all these possibilities and getting false positives. So that affects how many you're going to get wrong. Now, the paper itself, I'll give you a link to it, actually gives an example, presuming 20% will be right, 80% will be wrong, etc. You can go through the math of that. I have no time for that, and probably on the morning anyway. But it's those sort of considerations that that even if a scientist is being completely ethical, you're going to get that problem. Okay? Now, the problems further on about that are questionable ethics are still pretty common, but you'll see that next thing's more. So the more hypotheses are tested, the more chance you're going to get noise. Bigger samples are better. In medicine, because of the expense, you have small initial studies. Okay? The Wakefield experiment had, what, 8 or a dozen kids? That caused a disaster in terms of vaccination rates. Never mind that it was actually fraudulent data because of that too. Small effects are mistrusted. Because of the statistical noise, if you have a small effect, you should not trust it because the chance that the p-value accidentally allowed it to be significant is too high. Okay? And of course, you then need way bigger samples to determine if small effects are really real. Just outside the noise. We want to have multiple sources of types of evidence. We want to have consilience of different types of evidence. For example, evolution, you have fossil evidence, DNA evidence, a bunch of different types of evidence. They all point to the same thing that gives you confidence that you're right. The literature is on individual papers. Obviously, any individual paper might have a false positive. And there's also the problem of the publication bias. Pharmaceutical companies will often not publish studies that show that their drugs are not as effective. They spend millions and millions of dollars on these trials to say, oh, not so good, it's pretty close to placebo or equally placebo. Not going to publish that. It's quite rare to have actual fraud in terms of your data. It does happen, but it's rare. But this other thing, of not reporting trials because they're not favorable to your product, that's way more common. I'll show you a slide on that. So, and that's why you have to trust the literature on individual papers. The individual paper might show that your drug, antidepressant drug is going to work this much. But later on, you see other papers come on and say, well, actually the effect doesn't seem to be that big. And the effect size seems to drop as more studies are done. So you look at the whole literature instead of just one paper. And also, of course, because of bias, you want to have other people testing your claims to be yourself looking at the claims in your paper. And yeah, here, don't reject papers or fail to reject them all. There was a scandal over psychology papers, top journals having policies, not just practice, it just sort of happened. Policies against publishing publications. They would not do it, even if you're extending things a bit or whatever. Because there's been scandals about this, they reversed that policy. They're going to now start publishing publications. But that's the sort of thing we're dealing with here. So if you hear the desk door effect, which I mentioned before, people not publishing things that show negative effects or unpredictable companies. So the chances of dropping publishing 50%. Imagine that, millions and millions of dollars spent, but only half of those are actually published. Okay? So the trials with positive results are twice as likely as we publish trials with negative results. Using half of the evidence that we're supposed to be using to make informed decisions, and we're just missing the annual half, we're missing the alpha half. So again, I didn't put it on the slide or anything, but you want to do meta-analyses. Meta-analyses are done on effect sizes. Okay? You want to average all these effect sizes to see what the real effect size is. But you can't do that properly if you're missing half your data, and probably offsetting half your data. So even meta-analyses are affected negatively by the fact that you don't have all the trials published. So, to the solutions, all trials need to be pre-registered. So, basically, journals are supposed to commit to not publishing a trial unless it's been registered first. If you come in with a study saying, hey, we have a trial, look at this really means in fact cures this new disease. Journals are supposed to say, no, we didn't register it, we're not going to publish it. They've committed to that, some of them, but they violated it. They still publish some stuff that wasn't registered. And it's partly part of, like a culture that you get, volunteer peer reviewers and whatever else, and they're not told, okay, here's our policy now, understand it. If you get something that's not registered, don't even look at it first, just reject it out of hand. And there's also considerations as to whether or not ethics committees, even though they might not be funding you, there's funding committees and ethics committees. Basically, if you don't publish your trial within a year, you don't get funding. There's a proposal that they're doing with India, and also whether ethics committee would reject you as a researcher if you've been involved in trials that don't actually get published, because the effect on people's health, talking about medicine, can be as bad as purely fraudulent data. There's an ethical mindset that, okay, fake data is really bad. Nobody does it because it's obviously bad, it's against science. But this other thing seems to be like not in consciousness of people. And there has to be auditing before enforcement, because commitments aren't held up to sometimes. And of course, you must have replication. There's a senator in the U.S. saying no replication because it's overlap, have to save money, whatever. Replication is vital to scientific method. You must have replication. One, criticize pharma quite a bit, and they are sometimes quite evil, but the natural health people are worse. This problem. All these things have been treated, have been studied now by the National Center for Complementary and Alternative Medicine. All these things are being sold right now. At least with pharma, if they find that things are not working, or dangers or side effects that weren't reported initially, they get yanked. Or doctors stop prescribing it if it's only as good as the generic that was existed for decades. That sort of thing happens. But health food stores are still selling stuff, even though it's been studied and shown to be not effective. So they spent $2.5 billion as of 2009, and one thing they found that actually works with ginger. This is not 2009, but that's what I got from research today, yesterday. So it's probably about 250 studies about that year, I don't know. 250 products where they found one that works. But you don't see, health food stores selling only ginger. Yeah, so basically here you have small studies, cheap studies, they find a positive result and they run with it. They go put it in their stores right away, forget about it. Any studies that come later, again, they show progressively with better studies, bigger studies, less and less effect, so it gets to zero with the best studies. They don't accept that, the thing doesn't work. It's, pharma doesn't want us to know about these natural things. And there's a whole conspiracy theory behind that sort of thing. They're not knowing that big pharma owns big supplements. If you look at their annual reports, they list there the companies they own that sell stuff to health food stores. The same people. Okay, also with small numbers, another topic, side thing that people should know about that they don't quite think about very well. Very important for vaccine trials. These are rough actual stats, of actual risks. People say, it's very unlikely I'm going to get sick with or die from H1N1 flu. Very unlikely I'm going to get Grange syndrome, same difference, not going to get vaccinated. Here's what happens though if everyone does one thing or the other. In one city, everyone gets vaccinated. There's another one where nobody does. First one person will die because of the vaccination side effect. The second one, 1,000 people will die. Okay? 1,000 is a third of 9/11, for example, if you want to get your hype on to how important that is. Also, another thing that people seem to really don't get, both on the right and the left, people who are prejudiced and supposedly people who aren't, is that averages do not want to talk. I saw actually the bell curve. That happens all the time. I did last year, or 2 years ago, I did this experiment with kids, flipping coins, and saying, okay, how many got one head, two heads, three heads? We've got a bell curve. Okay? Happens all the time. This is the way things are. But somehow people think there's an average for this group and an average for that other group, and therefore everyone in that group is superior to the other group. These things overlap tremendously. And it's irrational to think of averages as being from monotonic data sets. And doing discrimination in that sense. And also, on the left, there's a reaction, again, because they buy the same paradigm as people who are prejudiced. They don't realize that if you stop studying things that shows differences between groups, you think, racially, racist, sexist, whatever research, they should stop it. Because when the actual demands for this research be stopped, they don't realize that these sort of studies can have tremendous beneficial effect on certain groups. Using comparisons between British children and Indian children, they found that there's a substantial difference in IQ. The racists will think, okay, that's due to genetics or whatever, and it's racism, and they're inferior, and I can feel better, even though I'm losing myself. My group is superior, so I feel better. That difference was actually caused by, partly iodine deficiency. Okay? It's part of your environment. In fact, you look at the firing, that's where iodine. If you don't do the studies between British kids and Indian kids, you don't know there's a problem. And then you don't try to find out why the problem's gone. Okay? You have to reject the paradigm, not the science. Okay, and also a big effect on girls. And yeah, the standard of living. I'm sure Indians would much rather have a better standard of living than some minority racists thinking they're inferior. Yeah, things are hard in statistics, but it's very important to not go with the theories that make sense to you, instead of what the data tells you. A big example of that is Spangheim-Volkov study on austerity. The stats showed that the Excel problem in their data, plus stuff that was biased data selection, was used as a justification for austerity in Europe, and even they were trying it here in the US. It turned out to be completely wrong. And that sort of thing could affect the employment rates of millions of people and the suffering, loss of houses, families breaking up, whatever else. This stuff is important. You don't just go with what you think because, families have to tighten their belts, so does the government thinking. Stats, you don't know what stats, so I'll just go with whatever I think. You have to look at the data anyway. It's hard, but it has to be done. Otherwise, it causes catastrophe. On sources, it's a paper. It's free, by the way, online. It's open source. So a better explanation of it. I took some of the points, and this blog is very good for learning about how to assess studies. This book, if you want much more in depth in this stuff, I haven't read it, but it seems to have pretty good reviews. And Medical Whittaker is campaigning right now to get all this stuff, trial registers and stuff like that to be done in the UK. And yeah, maybe see other ways you can find out more about this. Thanks very much. Over time, quite a lot, which I thought I would, but if you have questions, take them.
This is one of the biggest problems in terms of the public perception, that every time a new study comes out, the media reports it as if it is a definitive answer on that point, whether it's red wine or margarine or Dr. Lockdown last week. How do we deal with that?
Yeah, well, that's something for journalists. Since most studies are wrong, most breakthrough stories the journalists print are going to be wrong. And then people are confused, like, wait, you said butter is better. Orange is better than butter, and they're saying butter is better than margarine, and all this back and forth, which is what happens. Like, the research that needs to be done, things have to be replicated. But journalists always go with something spectacular to print, and they shouldn't. Part of their ethics should be to wait until something's replicated before they present it to the public. Looking at how much their ethics are influenced, how ethical they are in other areas, I don't think there's any hope for journalists to socialize all journalism.
Do you think that it's statistically possible to get closer and closer to an approximation of truth in society if the monetary system is no longer around, education is no longer around, if those two things, we have a resource-based economy and people are looking to thrive, do you think it's actually statistically possible to come up with numbers that bring us closer to the truth?
Only because, and I shouldn't have made the point, a bit of attention. Only because then there's not the profit motive to lie. With journalists, if it's sensational, they'll print it because it sells papers or people view their news show, whatever it is. So their motivation, the owner of that medium, is to get money. It's not to print the truth, right?
Right, but I'm talking more
But
about
so if you socialize things,
scientific.
you socialize things, it's under control, as long as you don't make the wrong government in charge, kind of thing. It's problematical, and it would help. There's studies showing that university research is less biased than corporate-funded university research, which is less biased than corporate-done research. That's not perfect, though. Even pure university research, funded by corporations, it still has a bit of bias. It's not too big. Significant. But it's not as bad as it could be. So it'll help, but it's not going to solve the